Okay, last set, and I'll start with a picture of a kitten. I'm maybe because I just watched the Legos movie, or I like cats or something. I don't know, but it just looks so hopeful, doesn't it? Either way, this is the last set. We're doing the final three problems, numbers 29, 30. No, that's 28, 29, 30. I'm not sure if I labeled the other ones right. I apologize. I'll go check really fast. Nope, looking at number 27 now, I realized that I had done a number 27 question on the last one, but I had not done 28. So I will relabel that so that it's labeled appropriately. So here's the number 28, picking up from the last set. A Gallup poll of 1,236 adults showed that 12% of the respondents believe that it is bad luck to walk under a ladder. What do you guys think? Is it bad luck to walk under a ladder? Does it make any difference? Consider the probability that among 30 randomly selected people from that set were polled, at least two have that belief. Given that the subjects surveyed were selected without replacement. So that what that means is that they, let's just imagine the whole crowd is standing outside some building, and they just threw a bean bag out, not a bean bag, but a little bag, tossed a bag. Yeah, that's what it's called, the little bean bag, not the kind you sit in it, not a bean bag chair. Into the crowd, someone grabbed it, and they said, okay, you come up here, we're going to ask you whether or not you believe it's unlucky to walk under a ladder. And then that person went back out into the crowd, and they threw another bean bag, and it could have landed in the same person's hand because they didn't say go home, they just sent them back to the group. So either way, hopefully you understand what without replacement means. So the events are not independent. The first person might be also picked the second time. Can the probability be found by using a binomial probability distribution formula, why or why not? So what they're getting at here is, and let me take us to the review page. This is the Triola Stats review page. Here on the right, they summarize the requirements for a binomial probability distribution. And it says that there must be a fixed number of independent trials, which you can think of those 30 as the fixed number, with all outcomes in two categories. And you can think of them in two categories. Their categories would be whether they thought it was unlucky to walk under the ladder or not. So whether they thought it was unlucky or not, two category, and a constant probability. And then we could use the numbers based off of the data that we have from the original 1,236 people. But what is also implied in here is that they are independent trials, right? So it's a fixed number of independent trials. And those are not on the surface. But then we have the law of large numbers that says if this sampling that we took, which is 30 right here, represents less than 5% of this total large number, then we can treat them independently even though we did it without replacement. So I'm guessing that it is less than 5%. So let's just figure that out. Here's 30, the sample size, the fixed size n, divided by 1, 2, 3, 6. And we get, I'll multiply by 100 if you feel, I don't know if you'd like to see that or not. We get 2%, less than 2.5%. So according to the law of large numbers, even though these 30 people weren't selected without replacement, they weren't selected in an independent way, we can treat them as if they are independent. And so I would say yes, all the requirements are met because I already explained how I think that you can consider them as two outcomes, those that think it's unlucky to walk on a ladder and those that do not. And there's a fixed number 30, so on and so on. So yes, although the selections are not independent, they can be treated as being independent by applying the 5% guideline. That's the using the law of large numbers. And then look through the other ones just to make sure. The selections are not independent. True, they're not independent, but we're going to use that law. The selections are not independent, and the 5% guideline is not met. No, it was, because 30 represented less than 5% of the total 1236. There are a fixed number of selections and can be classified in two categories, and the probability of success remains the same. It does remain the same as 12%, but we needed to use the rule. So I think they want us to go with the first one. That's what I would go. Determine whether the following probability experiment represents a binomial experiment and explain the reason for your answer. Well, going back to our list, and again, we can have this out in front of us during the test. Here's what we need. An experimental drug is administered to 130. There's a fixed number right there. Randomly selected individuals, they're all separate individuals, so they're independent in that way. With the number of individuals responding favorably recorded. Responding favorably. Oh, so the drug worked. Right, okay. So the drug worked or it didn't work. So there's your two outcomes. I think that's what they were trying to set us up for. So I'd say yes. Satisfies all the criteria. Number 30. Refer to the accompanying technology display, which is going to be right here. The probabilities were obtained by entering the values n of 5, p, and this is your constant rate of success, 0.793. Oh, that makes me want to go back really fast to number 29. No, because the probability of success differs from trial to trial. An experimental drug of 130 people, and they're given a number of individuals responding favorably. Yeah, but this kind of gets, this is kind of, in my mind, implying that there's only one trial. But if they were going from, if this is a series of trials that we obtain these 130 individuals, I would have to lean towards this. That is our other requirement, right? That the probability of success remains constant for whatever you're determining as success. And in this case, we're saying that the drug is working. You know, I'll fall back on that. Good thing we read on. Okay, so here we are given that P, which is already notation for the constant rate of success, is 79.3%. Okay, in a clinical test of a drug, 79.3% of the subjects treated with 10 milligrams of the drug experienced headaches. In each case, assume that 5 subjects are randomly selected and treated with 10 milligrams of the drug. Find the probability that at least 4 of the subjects experienced headaches. At least 4. Okay, we'll come back to that phrase. Is it unusual to have fewer than 4 subjects experience headaches? Well, let's look at the whole distribution when we make it. Oh, they've already made it for us. That makes life easy. Okay, so here is our binomial probability distribution. I actually want to show you what this would look like in StatCrunch. Let me see if I can do that really fast. Yeah, great. So, and I'll show you why you want to be able to do this. If we're answering the question, what's the probability that at least 4 subjects experience headaches? From the table we already had, what we had to do is just add the probability of having exactly 4 headaches and the probability of having more, which since there's only 5 for our number of trials, that would just be adding one more probability, these 2 probabilities. Well, that's not that hard for a phrase like at least 4 when there's only 5. That's 4 or more. Um, but what you can do is you can go into stats, calculators, choose the binomial probability distribution, and this is the last of our discrete ones we will look at before we start doing the next chapter, which go into the normal or the continuous probability distributions. So choose binomial. That was stat, calculators, binomial. I think it opened up here behind, so let me go ahead and grab that. When it opens, don't be deceived. Check your parameters here because, or sorry, what should I say? Check your fields here because it will start out with that default setting, with those default settings, and you need to fill in your fixed number of trials and your constant rate of success. By the way, don't you think this is so much easier to find out these numbers and get the table than to do all the work by hand, which we'd seen sometime before? And I will go back. If you're doing it by hand, you're going through this calculation right here for each one of those rows. So P of 0, P of 1, P of 2, P of 3, P of 4, P of 5, so 6 times. And even if you're using the calculator, like the TI-83 calculator, you would have been going through this set right here. So you can, anyways, I'll let you look back at that later, but it's the, where's the list? Binom PDF. And you can put an NP, and then this doesn't tell you, but if you want to stop at a specific point, you can put an NPX, and it'll be the exact value. I can show you more of that if you need it later. Okay, let me get back over here. Alright, so if I want to, I can say, what about starting from 4 and going greater than or equal to 4? So greater than or equal to 4, and that means basically 4 and 5, and adding those together, it's already added them together for me. And that makes sense, because if I add together, you know, about 40% and about 31%, I get about 71, but there's some little bit extra change here, so 72%. In fact, I can select that, copy it, paste it right on in, and then what do they want? 4 decimals? Okay, so let's just make sure we round 4. So if that is an 8, that will be a 9, and the rest will be gone. Excuse me. Okay, anyways, hopefully that made sense. If you're using the calculator, I could show you how to do it, but since they already gave us the list, I'm going to go that way. Incidentally, if I wanted to find out specifically at 4, I could put equals, hit compute, and it'll just highlight that one single item, random variable, and its corresponding probability. Notice that it matches. And I think it's really nice to see the distribution in this way because it is a discrete distribution as opposed to continuous, which we'll look at later. And the discrete distributions you can think of as like just being independent little stilts. Okay. So is it unusual to have fewer than 4 subjects experience headaches? Now that's funny, they turn it all around. This is having at least 4 headaches, at least 4 subjects having headaches, which is 72%. So what about the flip side of that? Is it unusual to have fewer than 4? That means 3, 2, 1, 0. Let me get that calculator out since I still have it and do strictly less than 4, fewer than 4. That means 0 subjects having headaches, 1, 2, 3. It's 27%. So I would say that's not unlikely. That means it falls in the usual range. So I would say, is it unusual? I'd say, no, it's not unusual. It's usual, so one of these two. No, it's not unusual. It's usual. Because the probability that having fewer than 4 subjects will experience headaches is unlikely. No, it's not unlikely. If it were unlikely, it would be below 5%, which that's not the screen I wanted, I'm sorry. Here it is. Having fewer than 4 is almost 28%. So let's go with it. Now your questions are going to be a little bit different, so don't hesitate to ask. And what do we have here? I went back on it and I shouldn't. For some reason I had a feeling like maybe I was not reading into it well enough. So I'm going to go back and say, of course it's wrong, but the experimental drug administered, this is one trial, so of course the probability of success remains constant in that trial. Let me go ahead and tally up my score. So I missed one there, I missed one earlier, and then 2 parts. So I think that ends up being about 2 1/3 if I add it all up. Which means, I've got 30 minus 2 1/3. I'd still get an A, 92%, but not what I'd like, right? I'd like 100. I'm not going to always get 100. I'm going to make mistakes. We're going to make mistakes. So I leave my mistakes here to show that there's nothing up my sleeve. We read these questions as carefully as we can, and sometimes we either psych ourselves out or don't read carefully. This one I should have stuck with my first instinct because there was nothing here to imply that this was trial over trial. This was one administration to 130 individuals as it was being written. Anyways, if there's any honest mistakes during the test, if there is something where you put 0.7228 and you didn't round correctly, even though that's an easy, we would probably agree it's an easy rounding calculation. But if you made a mistake there and you want to talk to me about it after the midterm, talk to me about it and I can make an exception. All right. So good luck, study, and do well on the test. Thanks.